Good morning, everyone. Good morning. This presentation will be about nuclear transmutations and mass defect and a simplified explanation with the help of the structured atom model. Yesterday we already had a poster session. There are two supportive posters for this presentation, so everybody can take a nice look at those again. And I would like to try to start with the findings/introduction, which I have scripted a little bit. The structured atom model is based on the idea that the nucleus has a stable and rigid structure that is responsible for all the attributes of the elements. The key point for this model is that we consider the neutron not to be a fundamental particle, since its decaying into an electron and a proton. Therefore, our concept is based on a proton-electron model rather than a proton-neutron model. Its physical properties and stability can be derived from its electrodynamic nature. There is no need for a strong force. Norman Cook, for example, has been working on a similar model in the sense that he also recognized a fixed structure for the nucleus on the phase centrifugal model. We have an overlap of ideas in some sensitive neutron not being fundamental and organization of the structure is different as a result of the neutron. The structured atom model is comparable, for example, to the alpha particle model in the sense that it also recognizes recurring geometrical structures inside the nucleus. The only difference there is that we still recognize a few more geometrical structures, which I will show later on, which in specific order and number create all the elements in their isotopes. So last year we attended the ICCF conference for the first time. So let me start that again. Last year we attended the ICCF conference for the first time, where we showed a partially complete periodic table of the elements. This year we are happy to show a completed periodic table with the structure depicted for every element. What we learned at the 2018 conference in Fort Collins last year was that we're definitely not the only one doing this. Many attempts were made to find logic in order to calculate the binding energy for all the elements. So we set out to take a good look at this topic of binding energy and how it relates to the structure according to the CERN model. And it should be, because it should work like all the other attributes. So the completed table allowed us to put all the elements in a spreadsheet and apply some simple rudimentary logic to this to see if we could find out how it works. We took each nucleon connection that is in the structure and multiplied that by the binding energy, which from deuterium, which is 2.225 MeV. The second method was to compare the known geometrical structures with their element and their binding energy. Meaning each geometrical building block, or nuclet as we call them, has a fixed known binding energy value. The tetrahedron represents the helium nucleus, for example, and has a known binding energy of 28.297 MeV. Every time we see this nuclet, we know the binding energy therefore as well. So the total is simply adding up all the different nuclets with their binding energy, and we will have a complete binding energy for every element. The graph that we plotted from that showed a few surprises. Next slide. So the nucleon method seems to hold true to a certain extent, but it is not very feasible since the structure morphs, as does the number of connection points between the nucleus. We resorted to the known first geometrical groupings, which repeat in the periodic table with known binding energy, and we were able to plot the calculated energy for all the elements from carbon 12 onwards. The correlation holds true, and we were happy with the results as it proved the structure as proposed by Sam. Because of our confidence in Sam and the strong correlation we saw, instead of assuming the approach, but beyond element 30, gallium, something happened. Both data lines started to deviate from each other. The SAM values became constantly higher. This trend continued until the end and is related to the change in the structure of the nucleus, which happens at this point in the periodic table according to SAM. Because of our confidence in SAM and the strong correlation we saw, instead of assuming the approach to be wrong, we looked at another reason. What we found offers a greater understanding of the fission and fusion processes. We can even offer a logical explanation how and why fission products are unequal in mass. A 70-year-old mystery can be solved with the knowledge of the structure of the nucleus. Fission appears to be breaking off parts of
breaking off of parts of the structure, branches as we call them, and they calculate the energy being released through this process. The branching structure of the nucleus results in internal stress energy, and this in turn is the explanation for the difference in the calculated SAM binding energy curve, which does not account for the branches and the actual binding energy values. Looking at the experimental results that are available in the public domain leads us to conclude that heavy stable elements can be made efficient under relatively mild circumstances. This presentation, for the rest, is meant to show you these findings. Here's the table of contents. I'm going to go quickly through the fission of uranium, a summary of the structured atom model. I will be going through that quite quickly. I cannot explain it. I do not have the time for that. We're going to show some nuclear reactions. We're going to go through the binding energy and an interpretation, some supporting evidence, and leave with the conclusion. So to start off with, here's the average binding energy curvature that I'm sure most are familiar with. It's just to summarize what is our current understanding of binding energy and mass defect. We can see, of course, the tip point is where iron and nickel are, the maximum average binding energy, and then it starts to slope up. The fission enigma. So the enigma is that when we have a fission of heavy elements, we get a very distinct double peak, not like a normal curvature, normal graph, with one peak, normal statistical deviation. We see two distinct points, and up to now, I don't think anybody has been able to offer a satisfying explanation for that. So the structured atom model basics. Before I continue, because I have a lack of time, I have way too much material to explain in such a short time, we will put all this material on our website where everybody can download it and read it back at your leisure. Okay, the summary of the structured atom model. We perceive a duality we call a proton-electron pair with the electromagnetic force acting between them. This force is the causal mechanism for the principle of the densest packing that creates geometrical shapes based on the platonic solidity. These geometrical shapes in a specific order and number create all the elements. The SAM shows the observed nature and the properties of the elements, and I would like to emphasize that the nucleus is not a lumped together collection of nucleons. The basis for this, the first building block, the first nucleus is the deuteron, and we recognize that, and there is no need, as I mentioned, for a strong force. So we use which we called the new neutron in the beginning, but now we refer to this material concept. This would be the idea of it. We get a 2.225 energy, binding energy. We plotted some information there, but this is the concept that we have for the structure. The first two elements, where we compare the standard model and the structured atom model. So, let's see, so here we have the deuteron, and here we have the deuteron, the structured atom model. This is a proton-neutron, this is a proton-proton, and an electron. Hydrogen-free, helium-free, helium-4. It's reminiscent of each other, yet there are some distinct differences. If we continue, we see that the periodic table has a cycle of 8. Every period is like 8 wide. And this is where we pointed that out. So we start with lithium, which is +1 value. We go to a beryllium, which is +2. Boron +3, carbon +4, or -4. There's a switch there. And then we go to the nitrogen -3, oxygen -2, fluorine -1, neon 0. So this is the cycle of 8, if you will. That is the basis of why the periodic table is created, or is as it is. So if we look a little bit further down, we see here the lithium and the sodium. And the lithium is the red lithium nuclide +1. The sodium still has that one lithium nuclide. The rest in white and green is always neutralized, meaning it does not participate in that sense anymore. You can see periodicity coming back, but there are also distinct differences which explain why, for example, in the oxygen group, oxygen itself is the outlier. It doesn't match with the other elements in the oxygen group. There are explanations there too.
In the groups, we can see again lithium, 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 or in the carbon group, carbon, 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 they all come back. Hence, the properties of those elements are also alike. Silicon and carbon are alike. And the noble gases, of course, which is all white and green, that's all neutralized. Everything is neutral, it's complete, it's noble. Doesn't need anything else anymore, it's on its own. So, this year, as I said, we finally were able to complete the periodic table, and it was quite nice. I was not aware of it. We found out, hey, it's the 150th anniversary of the periodic table, so it's a nice coincidence there. The shape of the larger elements. This is important at least to give you the concept of what we're looking at. What we can see here, it's, the structure, it's like an organic, what is it? Organic growth. It's very advanced. It's not a lumped together thing. We have in the center here, where I'm pointing right now, that's the first carbon nuclide. So each of those white groups is still a carbon nuclide. And in the center is the first one, and then you can add two more, and on the top of that one you can add two more, so you get a 1, 2, 4, 8 fractal, if you will, which I point out to the right. And here this is all exactly the same, so this is simply a fractal picture. This is already showing the nucleates, if you will, and here we just plotted the numbers of those nucleates. So notice that the first carbon is 12, and all the other carbon nucleates are 11. That is due to an overlap of one proton, one nucleon, which is part of both structures, hence it's -1, 11. Another important point is that there is a point of interference where the branches want to occupy the same point. And the point here, the carbon nucleate is blue, and on this side, that's where the next carbon nucleate should be growing. However, they are so close to each other that they will interfere, hence instability. That means at lead is the last, that's bismuth, is the last stable element. If you follow this logic, that means every other element after that is, per definition, unstable. That means also we conclude there is no island of stability. Observational data when we developed this program was neutron-proton ratio, valence or oxidation state, isotope stability, nuclear reactions, nuclear spin. These attributes, these observations were used to create the whole model. So, SAM, the next-gen model, it's a bit presumptuous, but there you go. In the past, we started out with a couple of models like the gas, liquid, shell model, alpha particle model, of course Norman Cook with the FCC model, and we believe that we are very close to each other, even though there are some distinct differences. The competition, so to put all these models that in the past century together, we plotted SAM there, basically go way back all to the central potential well model, meaning there's a central attraction force. Creates the sphere of the whole nucleus, if you will. So that's where we put ourselves. So the similarities and differences between the structured atom model and the FCC model. I would like to point out two major things. The FCC model uses protons and neutrons. This is of course the conventional thinking at the moment. Whereas SAM uses the protons and nuclear electrons. However, the overlapping is that both stipulate the stability of the nucleus is provided by electromagnetic force. Therefore, for stability, no strong force or strong interaction is needed. The stability of the nucleus, I would like to point out that when Norman Cook wrote a book with people like Dalla Casa and Paulo Lucia, and they conclude in their writing by taking the phase relationship into account when calculating the magnetic field effect of two circulating charges, an attractive force that exceeds the electrostatic repulsion of the charges is generated. A major component of the so-called nuclear force is therefore likely to be magnetic. And I believe that, where is he? Our friend over there yesterday has made a very good case for that as well. So. The differences between the SAM and the FCC model for specific elements. Here we point out the structured atom model on top. This is the alpha particle, if you will. The alpha particle will be the fourth And we show that oxygen in comparison to what Norman showed, calcium, zirconium, ytterbium, I believe it is, and lead. So note that the FCC model has a nested geometry, if you will, right? It's always one center and everything grows around that center, like an onion almost. There could be an island of stability in that model. We have, as I just explained, the lead/bismuth is the last stable element, therefore there is no island of stability. So we can see here the major differences between the models. We have an added-on or a structure of nucleates combining together, and this is the nested geometry. That's the major difference, I think. Pointing out nuclear reactions in SAM, I'm going to go in the next slides through these 5 topics here, from beta minus beta plus decay. I'm going to show a sequence of the alpha particle released from uranium all the way down to lead, quickly. Splitting of the atom, cluster fission, if you will, and fusion of nucleates, which is clustered fusion, i.e. cold fusion, LDR, etc. And as the last one, the Fourier cycle complete. So beta minus and beta plus decay. We have over here the neon 23, which is unstable. Take note that the light yellowish spheres are in the normal concept the neutrons, what we call the neutrons. Of course, we have to understand it's a proton-electron conglomerate. When we have 2 neutrons together there, they will form, 2 neutrons will perform beta minus decay, and then you get another pair there, which creates the next red, we call the lithium nucleate, and therefore it becomes +1. So this is the decay step of beta minus. Reversed, beta plus decay. We take away 1 from the sodium 23, we take away 1. We are left with sodium 22, then it's not stable anymore because it's unbalanced, and it decays into a neon 22, back to its balanced state. So this is, I believe, depicting beta minus and beta plus decay, the creation or the disintegration of the deuteron building block. Alpha particle decay. From plutonium 239, probably well known, you see on the left an orange structure there, and when that sheds 4 protons, 4 nucleons, which is the alpha particle, you're left with the situation here. So I highlighted where the change is to uranium-235. Another one, thorium-231, protactinium-231, which is a beta minus decay step. Then we get the next phase, actinium-227, thorium-227, radium-223, radon-219, radon-219 to polonium-215, lead-211, and then 2 beta minus decay steps again, and then a final alpha particle will be shed into lead-207, which completes the cycle and is now stable again. As you can see, here's that confliction, the conflict point, if you will. The red one needs to grow, as I showed in the period in the cycle of 8. It goes from lithium, beryllium, boron, carbon. So that's where the growth should take place. Take note there are 2 neutrons, if you will, still available. They will migrate to the center, take their place on the red part there, and then it can release again. So that's what you see here. And it can then release another alpha particle. Not happening. I think it froze.
Yeah, Greece is stable state.
We're back. So when we split the atom, we can see here as we depict uranium-235, and here are some potential fission products that come off. So you get an uranium, cesium, or a zirconium, barium. And here's the double peak again. So the zirconium would fall in the first peak, and the other 3 would fall in the second peak, which is around 140 AMU. Here we have uranium-235. We have a branch on the right, a branch on the left. I took them off of the nucleus. Take note that there is now a wireframe showing, meaning this is not a stable configuration, which is your fission product, which has to perform several internal transitions, yielding the energy, falling back to its ground state. But the point is that this structure, which is already in the uranium, which is basically the shape of the other normal elements that we know. So these red ones here, they decay, migrate to the center to make a more balanced situation, which leaves you with something like a cesium or an iodinium. The branches that come off, we believe that they first actually come together to collectively break off, forming the first peak. Now the numbers, 53 and 38, if you add them up, you're in that 90-ish, 100 region. The remainder is always in that 140 region range. Cluster fusion. So this would be the reverse actually of the fission process, which is what we deal with land. We can see here an oxygen and a carbon, which is often speculated on, that they come together in a silicon-28. So we show that it's pretty logical to get it together in that way. And yielding energy, of course, exothermic. Here's another one, palladium-105, which is very interesting because it's a noble metal. Noble metals do not oxidize on the air, and it does not because, believe it or not, the palladium is like on this side, exactly like an oxygen. On the right side, it's exactly like an oxygen. So palladium is like a neutralized big core with two oxygens added to it. So it would not be able to break up an O2 in the air because they're very, very similar. When we add a deuteron to the palladium-105, we can get a silver-107. So that should be an easy step. But understand that if we have several stabilizing neutrons not there, like in the isotope 104, it will not work and it will go to a silver-106, decaying back to palladium-106. Thorium cycle, which India is doing a lot of work on. We can depict that one pretty easily. You have thorium-232, the breeding process, plus a neutron, you get a thorium-233, beta decay to protactin-233, another beta decay to uranium-233, which you can use in fission. In reality, it's a bit more complex. They grow a little bit further. But the principle is, then you do perform the fission in your reactor. You're left also with a couple of neutrons again, which you use again to enrich the uranium-232. Binding energy. When we try to perform the binding energy as said, the first method was to simply point out all the connections, if you will, so you can call it a line of connection, and you can simply count them, and there's a logic there. It did not work really well, but approximately, yes, it works. And the deuteron has this binding energy of 2.225, and it's one line of connection, so simply multiply that. Here we see that first methods, simply calculating the total absolute binding energy. And the second method is the nucleates and their combination, meaning every nucleate, as I mentioned, has a known value of binding energy. That means in the bigger atoms, we can simply look at, okay, which one is there. So I have an example here of, in this case, the iridium-191. So we see the prime carbon, we see the center, there's one there, that's always there in the bigger elements. And the number of carbon nucleides, in this case it's one lithium, 9 neutral endings, a couple of extra neutrons, simply add it up, and you get the number of binds, which you multiply, and then you get your binding energy. Plotted that in a graph. This was quite surprising. We have a very strong correlation all the way up to about element 30, meaning iron, zinc in that region. And then the line started to deviate, which was a big surprise because, you know, it has to be either wrong, there has to be an error somewhere, or there's another explanation. So to show a little bit more detail, this is the delta between two elements. So from a hydrogen to a helium, there's a delta in binding energy, and then from the helium to the lithium, a delta binding energy, which we plotted here. In the beginning, you can see it's all really quite nice. Later on, again from that element number 30-ish, we see that there's a stronger difference between the two. That means what you just saw, the lines start to deviate. Every time you perform the next element, it deviates a bit more and a bit more and a bit more, but distinctly from this point on. So if we plot it in the accuracy or the deviation, if you will, Here's the first elements, which is very difficult to do. Other people will be talking about that today. We didn't strive for accuracy right now. We tried to find the logic first, right? Then we see all the way up to iron, zinc, gallium. There's a very nice correlation. And then it all the way suddenly starts to drop off. So the conclusions of this graph. The linear part is all the way up to iron and a little bit further even. The data sets correlate strongly. The deviation starts to come up. There are jumps in both lines, blue and red, which are unexplained. Like, I have to point that right there. There's a sudden jump. There's a sudden jump. There's a couple of jumps there, which are never explained by anybody, I believe. And if they do, please tell me. So, to sum it up, it seems that the elements have in actuality more binding energy than reflected in the observed values. We calculate too much. Could be wrong, but it could also be there's another reason. That's what we're going to. So when we look at the predictive capability even from the structured atom model, splitting the atom, we have a small calculation here, and we take the differences of the uranium for 235, for example, which is about 326 MeV. We plot the fission products, and in this case, promethium, I think, or I'm not sure, neodymium, and then you do the calculus, and you end up with 214 or so MeV, depending on what products you have. So I'm going to have to move on here. To point out another thing, here we have the depictions from Norman Cook's book, where you see the symmetry or asymmetry actually of the fission products coming off, meaning this is the 140 region, the 90 region, and they are actually completely mirrored, very, very nicely, very perfectly. We believe that is reflected in the structured atom model very nicely. And this graph too, which I cannot explain right now. A mass defect occurs in 3 instances, if you will. When you create a deuteron or a helium, you see a mass defect occurring. If you keep adding neutrons to a known element, you will also get that same effect. And as pointed out in the graph, in the heavier elements over here, you see the deviation, which is again that mass defect occurring. Supporting evidence. Supporting evidence comes from the Sapphire project. Very recently they came out with a new video. I would like to recommend that to everybody. It's highly fascinating, well done video. It's a pleasure to watch it, and they have some very interesting results. Quickly, this is their anode, which they use in their chamber, plasma chamber, before, in this case. Here it is after the experiment. And this is what they presented in that video, the elements that come off. And they were detected and validated by a US national laboratory. I do not know which one. A little bit more supporting evidence from Iwamura. We can see all these jumps here, lots of jumps, fission, fusion. I think both are happening. And then Mizuno, already working on this for a long time. Basically, the elements are all over the periodic table, so it has to be seen in our. Thank you. I'm going to conclude. One second. I need to do this. So we have discovered where and how much energy is hiding in which element that is represented by the stress energy or repelling forces between branches of the nucleus. This is a very new concept. The implications are that the topic of the binding energy is obscured in its relationship with mass defect. It's complicated, and it appears that the average dropping off of the binding energy or mass defect from iron onwards is in actuality the repelling force between the branches, which we call stress energy. You can see all the elements on our website in full 3D. Thank you so much.
We have a question. Bill started raising his hand first.
Do you have a figure of merit for the accuracy of your predictions, like an RMS deviation?
Please repeat.
Do you have a figure of merit for your mass estimations, such as the RMS deviation between the observed mass and the predicted mass?
Well, that's the whole point. What we're trying to point out here is that the mass defect, which we normally equate with the binding energy, generally speaking, is not that simple. What I'm trying to point out is that the mass defect, we're not seeing the real binding energy. We believe that the calculation, the logic holds true, but it's diminished by this repelling force. Hence, we see a lower binding energy stress.
So how do you test your model against reality?
Well, I believe that, well, this is the case I'm trying to make, that we can do the calculus, at least approximately right now. This is very new. And therefore, we can see that there is this, of course, it's the mass. ESMC square works, right? But we are not seeing it because, well, we're not seeing it, so we're not aware that there is in actuality, there is more binding energy in the nucleus than we think it is. So we believe that this topic is